welcome. This video, look at a combination of capacitors. I hope that the previous videos with parallel capacitors and series capacitors were fairly straightforward. Because in general, problems can be a little more complicated. In general, you can have combinations of capacitors. And in particular, we have one right here. Now, when I talked about series and parallel, I didn't explain why. I said, here's how you do it, not why. Well, for the parallel, what should have been evident is when you put capacitors in parallel, you increase the capacitance because the equivalent capacitance is the sum. What may not have been obvious, and we'll try to illustrate it here, when you put capacitors in series, your equivalent capacitance will always be smaller than the smallest capacitor you started with. So that explains the logic. In your supply, any electrical supply, you have a finite number of capacitors. But you may have an application that requires a certain value of capacitor. We haven't talked about application, but suppose you have an application that requires a certain value. So you have a lot of them, but just particular values. If you need a bigger capacitor, you put them in parallel, you get something larger than the largest capacitor you started with. You put them in series, you get something smaller than the smallest capacitor you started with. You combine series and parallel, you can kind of get some, intermediate value, whatever. So that's the logic of why you would have these combinations of capacitors. What I like about these problems in physics, it's not simply let's memorize an equation and do a calculation. For these combinations of capacitors, they're like puzzles, like logic problems. You have to work through them step by step. So it's a good exercise to do that. So let's do it for this particular combination here. You notice now, I'm not using pictures. These are all circuit symbols. There are three capacitors. You have the vertical bars or the horizontal. You have the 12-volt battery. You have the long bar for the high side, the shorter one for the low side. We're going to ask a few questions. One, now I have three capacitors. It's not pure parallel. It's not pure series. What is the equivalent capacitor? But then we're going to go deeper. We want to know what is the delta V, the voltage of each capacitor. What is the charge of each capacitor? That part of the problem, you're not going to find that part in the OpenStax textbook. You need to watch this video. There is no limit to the number of different ways you can combine capacitors. So you can't memorize one solution. You have to learn the principles, the logic, the steps. So for different combinations of capacitor, you can solve the problem. Okay, let's start. We'll do this as an example. Well, the question, where do we start? Well, if we look at these three capacitors, what stands out? What should stand out is that the 30 and the 18 are in parallel. We know they're in parallel because if I consider this side with one color, they're at the same potential. This side, another color, they're at a different potential. The two capacitors are in parallel and they have the same delta V. So we're going to start by solving those two parallel capacitors. Parallel is the simplest thing to do because we know C parallel is going to be the sum of the two capacitors. That's 30 microfarad plus 18 microfarad equals 48 microfarad. Notice the unit of capacitance is farad. Micro stands for 10 to the minus 6. We never worried about the 10 to the minus 6. If everything has the same power of 10, you just carry it through like part of the unit. I don't do any, 30 times 10 to the minus 6, 18 times 10 to the minus 6. Not necessary. Now, if one capacitor was microfarad, and another was millifarad or nanofarad, well, different powers of 10, you'd have to start fiddling with that. If everything is microfarad, everything is the same power of 10, you just leave it in there as part of the unit. So that is the parallel part. What I recommend here is let's replace those two with what the parallel value would be and look at it as a new problem. Okay, so here is the 12-volt battery. The 30 and 18 I now put as a 48 microfarad. I've replaced it. It's equivalent. I come around here. I've got my 24 microfarad. I go back. And notice what I said about parallel. You have a 30 and an 18. The combination is 48. The 48 is larger than the largest one. It's larger than the 30. Now we have a 48 and a 24. These are in series. How do I know they're in series? Because there's going to be a charge that leaves this battery. It's going to enter that. Going to go there. Going to go there. In series, whatever enters one must leave and enter the next, and leave the next one. So those are series. I'll clean that. So how do we solve series? This one is going to give, this will be our final part to get to the CEQ. So I'll just call that CEQ because it's going to give us the one capacitor. That's a reciprocal sum. 1 over 48. Again, I'm not going to worry about the power of 10, the micro, because I know it's microfarad. I'm just going to, I can write it there. I don't even need to write it, but I'll put it there. Okay. Now, you could get out a calculator, but I've set this up that it's simple enough. I can solve it just using fraction, common denominator. So I'm not saying that when you solve it on a test to go with fractions and common denominator. It's simpler, just use a decimal, add the two decimals, invert it, etc. But here I'm going to say that's 1 over 48 microfarad. The 1 over 24 is the same as 2 over 48 microfarad. So the 1 over 48 is there. The 1 over 24 is 2 over 48. So that's equal to, you have a common denominator, 3 over 48 microfarad. That's 1 over CEQ. So we have to invert the thing. We invert it, we get CEQ is going to be 48 microfarad over 3. 48 over 3 16 microfarad. I set it up. I could do the whole thing without a calculator, but test, you can use a calculator. 16 microfarad. Now I'm going to redraw this thing once again. Here's my 12-volt battery. This whole thing is equivalent to one capacitor, 16 microfarad. So now you see what we did. In series, the 16 microfarad is smaller than the smallest one of the two, right? I'm not saying of the ones we started with. The two in series, we had a 48 and a 24. In series, we get a 16. So the series allows you to get something smaller than what you started with. Parallel allows you to get something larger than what you started with. But we took these three, a 30, an 18, and a 24. Now we have 16. So it shows you how you can, mix and match like you're doing a puzzle, and you can get, some particular value. All right. So now we have CEQ. This is typically the first goal. CEQ, a lot of books will talk about how to do it. We want to go one step further. We want to solve for the charges and voltages in the circuit. So let's consider that now. We know that a charge leaves this battery. It's going to go to this capacitor, come back. What will that charge be? The charge that leaves the battery, remember this equivalent capacitor, this 116 microfarad is equivalent to the thing we started with, those three. So this charge is the charge that will leave in that circuit with the three capacitors. That charge, remember, it's the capacitance, which is 16 microfarad times delta V, which is 12 volts. Okay, here you could use a calculator. 16 times 12 is 192. Let's look at the unit. We have microfarad, we have volt. What do we do with that? Well, what's the unit of charge? The unit of charge is the coulomb. Now we kept the micro in there. It's really 192 times 10 to the minus 6, but I don't need to convert that. I'm just going to say this is equal to 192 microcoulomb. Remember, C has been used twice. Sometimes in the unit it means coulomb. Sometimes in the equation means capacitance. Here it's 192 microcoulomb. So we know that 192 microcoulomb left that battery, went through the circuit, and came back. So if I go back to my previous picture, I can say the same thing here. The charge that left this battery went to this capacitor, went to this one, came back. So therefore, in series, you get the same charge on each one. So this has 192 microcoulomb. I'm sorry, it should be a coulomb, not an F. Microcoulomb. Hope I had that down here. Yeah, microcoulomb. And in series, this one will also have 192 microcoulomb. What do we do with that? Well, now I can solve for the voltage. Remember, the equations are straightforward. It's the logic, the steps, how do I apply them? We know that for a capacitor, Q equals C delta V. Therefore, delta V equals Q over C. So for this 24 microfarad, I can say delta V, the charge 192 microcoulomb divided by 24 microfarad. Micro will cancel out. 24 to 192, again, there's a calculator problem. If you figure that out, you'll find out that 24 goes into 192 8 times. The micro cancels out. You have 8 coulomb per farad. You say I'm measuring delta V, so it must be 8 volts. The context tells you it's volt. Units tell you it's coulomb per farad. So now I know this capacitor has 8 volt on it. What about the other one? Well, the other one is going to be 192 48. So let's go over here. And so if I had a voltage for a capacitor was 192 microcoulomb, and the capacitance was 48 microfarad. Well, 48 goes into 192 4 times. Micro cancels out. Coulomb per farad. I'm measuring delta V, so it must be 4 volts. So this capacitor is 4 volt. Okay, but this is not what I started with. Let's see what I started with. Well, the 24 is right here. The 24 has 192 microcoulomb. The 24 has 8 volt. What about these two in parallel? Well, what I know is there's 4 volt across that part of the circuit. See right here? The 48 has 4 volt across it. Remember, in parallel, everything has the same voltage. So there's 4 volt across that 48. There must be 4 volt on that capacitor, 4 volt on that capacitor. Again, I'm going to make the point, we're not simply saying here's an equation, let's do a calculation. This part of the course, this kind of problem, it's all about thinking about how do I apply the rules, how do I do the logic, how do I work it out. There are equations, but you have to figure them out step by step. Now, how do I get the charge? Well, remember, the equation is straightforward. The equation for the capacitor, Q equals C delta V. So the 30 microfarad Q, let's say I've got C is 30 microfarad and delta V is 4 volt. So the charge 4 times 30 is 120. Is microfarad volt. What could that be? Well, the micro just means 10 to the minus 6. Unit of charge is coulomb. So that charge must be 120 microcoulomb. So put it right here. This capacitor, clean up some, has 120 microcoulomb. What about the 18? Well, the charge on that one, the charge on this 18 is going to be, it's not the same Q every time. Let's just call it Q, the Q for the 18, and this other one was the Q for the 30. Okay, so the Q for the 18, C delta V. Capacitance is 18 microfarad. The delta V is 4 volts. 4 times 18 is 72. 72. Microfarad volt. Again, micro 10 to the minus 6. Unit of charge is coulombs. So it must be that this, what I called Q18, the charge for the 18 microfarad is 72 microcoulomb. Let's enter it here. 72 microcoulomb. So now I'm going to clean this up. Let's get rid of all this over here. All this over here. And see what we're left with. Some of this too. Now we know everything about the circuit. We have a 12-volt battery. We have a 30 microfarad capacitor with a voltage of 4 volts, 120 microcoulomb. 18 microfarad capacitor, a voltage of 4 volts, 72 microcoulomb. Notice the two in parallel have the same voltage. If you sum up the charge, 120 and 72, you get 192 microcoulomb, which is what the charge was when I said that those two were equivalent to a single capacitor. A single capacitor was a 48 microfarad with 4 volt, 192 microcoulomb. Here we have two in parallel, 4 volt, and there's the 192 microcoulomb. The 24 microfarad has 192 microcoulomb and 8 volt. Of course, the other part of the problem was CEQ, 16 microfarad. So this kind of problem, you want to practice it and study it because there's so many questions. I could write the circuit differently. I could arrange the capacitors differently. I could put different values of capacitors. I could put more capacitors. I could ask, what is the equivalent capacitance? What's the voltage on this one? What's the charge on that one? So you need to learn the equations, but it's so critical to practice because you want to think through the rules. If you write down this circuit, work it out by yourself, thinking each step, parallel, same voltage, series, same charge. For a capacitor, Q equals C delta V, or delta V is Q over C. So many steps you have to take. You know, draw the circuit, redraw the circuit, simplify, etc. So this one, I recommend you practice this. There's no limit how many different circuits you can draw. So you really want to focus on understanding the rules for working out the problem. Okay. I thank you for watching all the way to the end. And that concludes this section on combining capacitors. We'll come back to some similar principles in the future when we talk about combining resistors. But for now, we're going to conclude this video, and I thank you for watching all the way to the end.